Hey guys, it's time to continue with our Learning at Home series. So last week we finished up with the Jovian planets, so we've taken care of the solar system as far as the planets go. But there's still a lot of stuff in our solar system. We have asteroids, we have meteors, we have comets, and these are the things that we're going to be talking about for the next couple weeks. So today I'm going to go over asteroids and meteors, and then next week we'll pick up with comets, and then we'll go from there. So let's go to asteroids and meteors. So asteroids, they're often called minor planets. They are objects that are not the planets proper and not comets. So they're big rocks, but they're not that big. And this is important. They're believed to have formed in the same way that the planets did. So they would have formed around the same time the solar system did, from that same disk of solar nebular material that was accreting, just becoming slowly larger and larger rocks. They range in size from 1 meter in diameter to 1,000 meters in diameter. So from kind of small to really, really big. The largest ones are very similar to tiny planets. So you can see down here, there's a chart showing you like how many there are of about each size. Asteroids with a diameter of less than 1 kilometer or 0.1 kilometer, there's about 25 million of them. And remember, these are just estimates. Then you start getting into the larger ones, 50-kilometer diameter, about 600, 200 kilometers, 30, 900 kilometers, 1. And that's a very special one that I'm going to point out to you. Types of asteroids. So there's many subtypes of asteroids. I'm going to go over the 3 biggest categories. So we have our C group. C stands for carbonaceous, meaning they're mostly carbon. This is 75% of your asteroids. Since they're mostly carbon, which is a really dark, not reflective material, think of like what carbon fiber looks like, coal, things like that are high carbon. They're not reflective. They're really hard to see. So this would be a good image of a C group asteroid. This is the majority, the vast majority of your asteroids. Next, S group. S stands for stony. So these are rocky. They have more minerals to them. And since they have more of these silicates in there, they are more reflective, meaning they're brighter. This is 15% of your asteroids. So we only have about 10% of them left. And the rest of them kind of just get thrown into a catch-all group called the X group. They're mostly metallic, though. Since they're mostly nickel iron based, they tend to be the brightest ones. Metals are the most reflective. So you went from having carbon to having rocks and minerals to metals. So these would be the easiest to see. They're the most reflective. Now, where can you expect to find them? Hopefully, you immediately think of the asteroid belt. So this big white area right here, the asteroid belt. It's in between Mars and Jupiter. So the majority of them are located there, including the largest asteroid. But of course, there are asteroids found in other places. They are sometimes found in the orbits of planets. So they're found in the orbits of the Earth, especially Jupiter, since it's the largest planet, has the largest concentration of asteroids in its orbit. And we'll talk about that specific population later. So the asteroid belt. Clearly, this is just an artist depiction. This is not a real picture of the asteroid belt. In fact, as you'll see, this is actually a really incorrect way of seeing the asteroid belt. So it is the largest collection of asteroids in the solar system, but 50% of its mass is concentrated in just 4 asteroids: Ceres, Vesta, Pallas, and Hygeia. 50% of the mass of the entire thing. So it is often said that it possibly could have formed another planet, but this is untrue. So the asteroid belt is in an area where another planet could be, but what's left there is not nearly enough mass. For this to be true, the idea is that Jupiter would have had to flung most of that material out of the solar system, leaving what we have today. But as it is, the asteroid belt could not have formed to be a planet. The asteroid belt has only 4% of the mass of our moon. So most of that mass, if it was going to be a planet, would have been thrown out by Jupiter. As it is, though, it does not have enough mass to make a planet. This is how you guys often think of the asteroid belt and are shown it, I'm sure. This, though, is really incorrect. The asteroid belt is really sparsely populated. Asteroids are very spread out. The biggest ones, millions of miles apart. And little ones, even then, they're thousands of miles away from each other. The asteroid belt, contrary to how it's shown in like sci-fi or in images like this, would not be an area where you gotta like maneuver your ship all around just to get through the rocks and not be crushed. You'd be very easily able to just fly right through and maybe not even see one. But the largest asteroid does live in the asteroid belt, and that would be the queen of the asteroid belt named Ceres. Ceres, being the largest asteroid, was the very first one we found. And it's now considered a dwarf planet. Looking at it, it looks like maybe Mercury. It is the only object in the entire asteroid belt that's actually got enough mass to gravitationally shape itself into a sphere. Remember, to be shaped like a sphere, you have to have enough mass to have strong enough gravity to make that happen. This is the only asteroid that we're aware of that does in the asteroid belt. It's also the only dwarf planet inside Neptune's orbit. Anything else that's considered a dwarf planet is farther away than Neptune, like let's say Pluto. And it's about 1,000 kilometers in diameter. Here's a size comparison: Earth, Moon, and Ceres. So you can see quite a bit smaller than even the Moon. Here are the 4 largest asteroids. This right here, these 4, this is 50% of the mass of the asteroid belt, concentrated in just those 4 things. And you can see Vesta, Pallas, and Hygeia. They all have that oblong potato-like shape to them because they don't have quite enough mass to make themselves into a sphere like Ceres does. Now, that population of asteroids I mentioned that kind of sits in the orbits of planets, they are called Trojan asteroids. They are asteroids that share an orbit with a larger object, often planets. So here's that image I showed you before. There's Jupiter on the bottom left, and you can see these chunks of green dots. Those are the asteroids that share Jupiter's orbit. Some are in front of Jupiter, and some are behind him. Now, they settle in specific areas. You notice the way they kind of are like that in the 2 corners in front of Jupiter and behind Jupiter. Those are actually special areas called Lagrange points. They're areas where the gravitational forces balance in a way where something in that spot will stay in that spot relative to whatever it's orbiting. We use this quite a bit when we put things in Earth orbit. So we put something in a Lagrange point, and it will remain in that spot as it orbits the Earth. So it would always be there relative to the Earth. And specifically, we have them at L4 and L5. So these 2 areas right here where you're going to find your Trojan asteroids. So there's Trojan asteroids in front, and there's the ones behind. That angle will always stay the same. So as Jupiter orbits, the asteroids in front keep moving in front of him, and the asteroids behind him keep moving behind him. They will always stay at 60-degree angles relative to Jupiter. Now, Jupiter is not the only planet that has these asteroids hanging around it. Earth does too. This right here shows you all the asteroids that we're aware of around the Earth. So there's the sun at the center. Mercury is the brown circle. Venus is the purple. Earth is the white circle. All of these dots are asteroids. So the solar system isn't as empty as we probably think of it. Now, since they're near the Earth, we call them near-Earth asteroids. They are asteroids whose orbits bring them near Earth. Just because they are near us does not mean they are harmful, though. So we have a designation, potentially hazardous objects. Not all near-Earth asteroids are potentially hazardous objects. We have 4 classifications, and they're based on their orbits. We have the Atiras, the Attens, the Apollos, and the Amors. If you notice, Attens and Apollos are both in red with PHO next to them. PHO stands for potentially hazardous objects. These two are potentially hazardous to the Earth. And if you look at the picture on the right, here's why. The sun is at the center here. Earth orbit is this blue circle. Notice the blue circle intersects these two white circles. This tells you the Earth's orbit crosses the orbit of these asteroids. That is potentially dangerous. If the Earth is right here at the same time an asteroid is right here, we will collide. So that's potentially dangerous. Now, it's very, very possible that we can cross the orbit just fine and there's no asteroid right there. This happens all the time. Earth crosses these orbits and we aren't necessarily impacted by anything because there's not literally asteroids everywhere in this orbit. It's just potentially dangerous because if we're in the same place at the same time, that can be a problem. But don't worry, because we monitor these things. Around 1998, we began tracking as many as we could find. NASA and the European Space Agency monitor them constantly. We've detected over 19,000 of these things. All the dots you're seeing on this animation are the asteroids that we've been detecting as time goes on. 50% of what we've detected are Earth orbit crossing Apollos. But even though they cross their orbit, remember, that doesn't mean they're going to hit us. But even then, we still take a closer look at the ones we consider especially dangerous, like 101955 Bennu. Bennu is considered the second most likely near-Earth asteroid to strike the Earth. If it did, it would have the power of 80,000 times the Hiroshima nuclear weapons. This is Bennu. So Bennu, as you can see, is kind of a rocky, weird-looking asteroid. We have a mission orbiting it right now. It is the OSIRIS-REx. So this probe is designed to actually orbit, end up capturing some samples, and then return them to Earth. So it is going to bring material from this asteroid back to the Earth. So we're going to study it, hopefully learn a little bit more about the asteroid, maybe potentially how we could deflect it if necessary. And I mentioned before that a lot of these asteroids would have formed around the same time the planets did at the beginning of the solar system. So asteroids are like time capsules. We could go back in time and see what things were like at the beginning of the solar system by looking at material from things like this. Now, even though this is the second most likely near-Earth asteroid to strike Earth, it still has like a 1 in 2,700 chance of impacting the Earth in about like 175 years. So it's not a guaranteed event, and it's not going to be happening within our lifetimes. So here are more images of Bennu. This is an even closer up shot from OSIRIS-REx. And then here you can see just the very craggy landscape. It's like you rolled it in sand and it's got all these little particles attached to it. This is what they're going to collect and bring back. All right, meteors. So meteors are actually one stage of a three-step life cycle. So we have meteoroids, meteors, and meteorites. I feel like this is unnecessarily confusing, but this is how it works. So there are three stages in the life cycle of these things, and it depends on where it is. They begin life as just little rocks in space. If they go from as big as a grain of sand all the way up to almost an asteroid, we would call it a meteoroid. So when something is in space, when you have a small rock in space, it's a meteoroid. If it's not an asteroid yet, you call it a meteoroid. If it's once it reaches a certain size, you would start calling it an asteroid. But if it's less than, let's say, a meter in diameter, we would call it a meteoroid. But once that meteoroid hits the Earth's atmosphere, it's going to start heating up. And the reason for this, we've talked about when spacecraft return to the Earth, they have heat shields to protect them from all the heat. Like as they're going through the air, it produces a lot of pressure and friction on that object. It's going to cause it to heat up. But when it heats up, it starts to glow. So something like a shooting star, we often call them. This is the meteoroid heating up as it enters the Earth's atmosphere. Once it does this, it gets another name. Now we call it a meteor. So when the space rock enters our air and heats up, it's called a meteor. So we started with rock in space. If it's just in space, you can call it a meteoroid. Once it enters the air, it's a meteor. And if it reaches the ground, it becomes a meteorite. So 3 stages. Meteoroid is in space. Meteor is in the air. Meteorite is on the ground. So remember to keep those in order. Meteoroid, meteor, meteorite. So meteorites are just solid debris that actually managed to hit the ground. So they range from size from something absolutely tiny. This is someone's roof. There is a tiny little crater left behind by a meteorite. Here's a tiny meteorite. So they can be very small, or they could be quite large. You may not have noticed the kids sitting inside of this meteorite. So they can be huge. This right here is the largest meteorite that's been found on the Earth. And when they hit the Earth, they usually leave a crater that's 10 to 20 times the size of the meteorite. So this guy, you can imagine, would have left quite a big crater behind. Here's someone's car that was unfortunately hit by a meteorite. Hopefully his insurance covers meteor damage. Now, speaking of impacting the Earth, obviously we are aware of even larger asteroids out there. We're watching a bunch of them. And we can calculate the probabilities of them hitting the Earth. Remember, probabilities are not guarantees. So for a 1 kilometer diameter asteroid, the probability is about 1 every 500,000 years. 5 kilometers, 1 every 20 million years. And 10 kilometers and up, 1 every 70 million years. If each of these things were to happen, 1 kilometer diameter asteroid, you're looking at like city devastation. Like if one hits the city of Houston, it's going to be a mess for quite a while. The rest of the country will be relatively okay and will be fine. 5 kilometer diameter, you're looking at wide regional destruction. So that would be able to destroy, like, let's say, a good swath of North America. Now, it's not going to completely obliterate it, but it will have widespread damage such as, dust thrown up into the air, wildfire production, acid rain, things like that. 10 kilometers, you're looking at global devastation, mass extinction events. So hopefully that's reminding you of the most famous asteroid impact, the Chicxulub impact. So the crater is discovered in the Yucatan Peninsula. So the Chicxulub crater is the leftover crater from the impact that killed the dinosaurs. So this is the latest mass extinction event in Earth's history, about 66 million years ago. We are pretty sure it was caused by an asteroid between 10 and 80 kilometers in diameter. Giant range. And it would have released between 21 and 921 billion times the energy of the Hiroshima nuclear bombs. So it would have been instant vaporization for anything in a gigantic radius. It would have likely caused global wildfires. It would have thrown enough dust into the air to block out the sun for over 10 years. It would have dropped temperatures by 20 to 30 degrees Celsius. Plant life would have died because it wouldn't have been able to get sunlight. Herbivores would die because they wouldn't have plants. Large predators would die because they wouldn't have the herbivores to eat. Destruction of the food chain. Massive problem. That's why it was a mass extinction event. Now, this picture right here, this is the smoking gun. So this was the piece of evidence that really led people to say, oh, it was an asteroid impact. This right here is iridium. And this was found all over the world at a certain depth. And remember, like when you dig, the deeper you go, the farther back in time you're going. So if you dig down deep enough, you're seeing far back in time. So if you find this all over the world, and if you're finding this high concentration of iridium, which is a metal that's not commonly found on the Earth, but commonly found in space and asteroids, and you're finding this high a concentration literally everywhere in the world, it's telling you that some global event happened that brought a material uncommon to Earth, but common to space. So this is considered the smoking gun. It's called the Cretaceous Paleogene boundary. So this right here, this layer of iridium, is the evidence, the big evidence that led people to believe an asteroid killed the dinosaurs. And then later we found the crater in the Yucatan. So asteroid impacts have happened. They're uncommon. And of course, now we are actually monitoring for these things. So that is all I have to say about asteroids and meteors. So remember, this is just a quick overview. This is not obviously everything there is to know about asteroids and meteors. I will be giving you guys a quiz on Wednesday over this stuff. So make sure you watch this video, and we will pick up with comets next week. If you guys have any questions, let me know. I'll be doing Zoom office hours on Thursday if you want to stop in and ask your question then. And be sure to like and subscribe, and I'll see you guys in the next one.